Hey guys, today our video, I'm going to try to do this super fast because I just spent a lot of time recording this and for some reason my microphone was not working, so there was no sound picked up. So we're going to fly through this. Today we're going to talk about Kepler's Laws of planetary motion and Newton's Law of gravity, which is something you guys should know from last year. Alright, if you don't know much about Kepler or Brahe, I suggest if you are just interested in Renaissance astronomers to check them out. Both of them are pretty cool guys. But Kepler did a lot of work explaining planetary orbits with Brahe. They worked together. And there's a little bit of drama in the astronomy community about whether or not Kepler stole Brahe's ideas. But the fact remains we call what they developed Kepler's Laws of planetary motion. So, let's get into what they say. Here are the three of them, and I'll go ahead and if you guys want to pause and scribble them down. I'm not sure if that's really required because we're going to talk about them a little bit in further detail in a few seconds. But this is very scientifical speak, and I'm going to tell you guys a little bit easier way to think about it here in a second. Alright, so the first one says that a planet's orbit around a sun is elliptical. How elliptical that orbit is something that's called orbital eccentricity, and we denote it with a lowercase e. If you have an eccentricity of 0, that means that you're a perfect circle, and 1 means that it's pretty much a straight line. So most of the planets fall in between this area right here. Circle and medium eccentricity. Most of the outer planets fall in here. The inner planets, their orbits, when you look at them, you would think that they are circles, but they're actually not. They're just very slightly elliptical. So, because this is an ellipse, however circular it may appear, the sun is at one focus here. And because the sun is at one focus, as the planet moves around, there are areas or times when it is farther away from the sun, and then areas and times when it's closer to the sun. We call these regions perihelion when it's close to the sun, and aphelion when it's far away. So the second law, a way to talk about the second law is to say the law of equal area. And the second law says a line joining a planet and the sun sweeps out equal areas in equal time. This means that planets travel faster at perihelion and slower at aphelion. They're going to travel faster when they're closer to the sun, and they travel slightly slower when they're farther away. So here's a little graphic that I have to show you guys this, and essentially if we look at this portion of the planet's movement here, let's say we're starting here and we're moving to here. As the planet moves along this arc length here of its orbit, it's going to cover this amount of area in space, denoted by this light green triangle that I'm now coloring red. This is a particular area, and let's say it did that area in a particular amount of time. Well, over here, when the planet is in perihelion, or closer to the sun, now it has a shorter distance away from the sun. So in order to cover the same area, this is like a long skinny triangle. So over here we need to do a short fat triangle here. In order for these green regions to be equal in area. So that means that if the planet wants to cover this much area here and this much area here in the same time, it's going to need to cover a much longer arc length here in order to do that. So the only way the planet can do that effectively is if it gets faster. It has to get faster because it's covering a longer arc length here than here, even though the areas are the same. Alright, law 3 is the one that's kind of a jumble to say, but a good way to think of it is in simpler terms, is to say that planets that are closer to the sun have shorter years than planets farther away from the sun. A lot of these rules are going to seem like simplistic to us and things that are kind of no duh, but at the turn of the century, 1500s, 1600s, these were pretty remarkable discoveries. So again, here is our little diagram of a planet and its orbit. Here is the line representing the major axis. So the length of a planet here depends on the length of this axis. The longer this axis is, the longer the year. The shorter the axis is, the shorter the year. Alright, so for problem solving purposes, a couple of terms we need to discuss. The first, I'm not sure how comfortable you guys are with astronomy units, but 1 AU is called 1 astronomical unit and it's the distance from the Earth to the Sun. We in astronomy have just arbitrarily called that 1 AU, and that distance is approximately 1.5 times 10 to the 11th. Remember, the Earth is making an ellipse around the Sun, so it's not this far away from the Sun all the time, but on average, this is the distance, and we call that distance 1 AU. It equates to about 93 million miles. So, if we wanted to talk about the third law mathematically, this is what we would say. The square of the year is equal to some constant. This is a constant that's the same for all of the planets, times the length of the axis cubed. So let's just do a little example real quick so that we can just see how this all pulls together. And I was going to go to my whiteboard, but it doesn't seem like it wants to do that, so I'll just do it up here. So let's look at Neptune. Neptune has a period, that's what the T stands for, period or time for one complete revolution. A period of 164.8 years. So my question is, how far away is it from the Sun on average? So let's look at the third law. So third law says T squared equals CR cubed. And remember that C is a constant that is the same for all planets. So if I was going to rearrange this, I would get T squared over R cubed. This is the constant that's the same for all of the planets revolving around our Sun. I should make that denotation here for what we're about to do later. So that means that if I can find what this constant is equal to for a planet that I know, I can use that constant up in here for Neptune. So we're just going to go with Earth. So the period for Earth to go around the Sun is 1 year. And the distance the Earth is from the Sun is 1 AU. So that makes our math super easy. So that's just 1. So when we come back up here, we have the period 164.8 squared is then equal to radius cubed. So I know some of you guys are like, why is the C even there? That becomes important for what we're going to talk about in a second, because we might not always be concerned about the Sun and a planet. We might be concerned about the Earth and a satellite, or the Earth and the Moon. And so C becomes something a little bit different at that point. But for planets around the Sun, it's 1. So that means that our radius, whenever we do this, is approximately 30 AU. Now, some people might have been worried about converting this into seconds or whatnot, but as long as your constant has this units, years, and AUs, I can use years here and AUs here and be perfectly fine. Just make sure that the units that you're using match up to whatever it is your constant is. Okay, so Newton's law of gravity, we talked about this a little bit last year. Kepler did a lot of work with talking about how planets move, but Newton was the first one to come along and actually describe why. And I know maybe as a elementary school kid you guys were taught that Newton discovered gravity, but he didn't really discover gravity. It was always there. Newton was just the first person to put gravity in space, to say that the fact that these huge objects have mass, this is why gravity exists. So Newton's law of gravity says there's a force of attraction between any two objects with mass. And this is what it looks like. We did this last year, but the force of gravity is equal to gravitational constant m1, m2 over r squared. So your two masses over the distance between them. G is your gravitational constant. Here is what it's equal to. And this number is on your formula chart as well, so you don't need to memorize it. So let's do this quick little pluggy and a chuggy example. Find the gravitational force that attracts 65 kilogram boy to a 50 kilogram girl when they are 0.5 meters apart. So F, G, 65, 50, 0.5 squared. All right. We plug all this in, we put in this number here for our G, we should get a very small number, 8.67 times 10 to the negative 7th newtons. The only thing I really want to drive home is please watch your units. Your gravitational constant is in kilograms and meters, so please make sure your masses are in kilograms and your distances are in meters. That's probably where you guys are going to mess up, if you mess up at all with this particular relationship. So the gravitational force between two objects is really, really tiny. The only time when you actually notice it is when one of those objects is very large, like on the order of a planet. But I want to talk about this quick example because it might show up later date. Let's talk about a satellite orbiting the Earth here. Now, we know that for objects that are stuck on the surface of the Earth, the acceleration due to gravity is about 9.8 meters per second squared. But, of course, the farther you get off the surface of the Earth, and once you get into outer space, this acceleration is going to decrease because you're farther and farther away from the planet, which makes sense. You're farther and farther away from the planet's center of mass, which is where all this stuff is calculated from. So, if this was my satellite and I wanted to figure out its acceleration at this height above the surface of the Earth, what I could do is I could say, okay, well, I know that net force is equal to ma. And for my satellite here, its net force is the gravitational force between it and the planet. So g m1 m2, and we'll say that's m1, equal over r squared equals m1a. So I've got m1s on both sides, and then my acceleration just becomes gm2 r squared equals a, where m2 is the mass of the planet, or the mass of the object that the satellite is orbiting around. Okay, so if we assume a nearly circular orbit, which is what we're going to do next, it's possible that we can combine the two, Newton's and Kepler's laws, to have a value for the period of a satellite, or the period of something that's orbiting around something else. I'm going to tell you this relationship could be helpful to have as a programmable equation. I've seen it on an FRQ once in the past 10 years. That's not to say that they're not going to do it again, but I want to at least have you guys introduced to the concept. So let's talk about let's do it with the sun here and the Earth. So we're going to, like I said here, assume a circular orbit, because if we don't, then that makes our math really complicated and gross, and we're not aiming to do that right now. So, circular orbit. The Earth here, as it's orbiting around the sun, it's experiencing a force, and that net force is ma. Now that net force is coming from the sun. It's a force of attraction between the Earth and the sun that is keeping the Earth in its orbit. So that's our gravitational force. But this gravitational force is also doing double duty as the centripetal force, keeping the Earth going in a circle. So I'm going to say mass of the sun, mass of Earth, r squared. And this gravitational force is equal to the centripetal, which is mv squared, m Earth v squared over r. Now I can kind of do some combining here, cross off some common terms, have m on that side, I have r here and an r here. So when I rearrange this, I can say g ms over r equals velocity squared. So this velocity, remember, this object is traveling in a circle. So if I wanted to talk about its velocity like that, I could say that its velocity is its distance divided by its time. In this case, the distance is going to be the circumference of this circle that it's creating. And the time it takes it to do that is going to be its period, or the time it takes for one complete revolution, which is t. So once I come up with this idea for my velocity of the object traveling in a circle, I can plug that in down here. Let me erase that real fast. Now remember, I'm going to square it, so I'm going to take a jump in my algebra real fast here for the sake of time. Squared r squared over t squared. Again, I've got some like terms I can combine. I can cross multiply, bring the r over here, I can bring the t over here, and then when I rearrange that, what I've got, hopefully if my pen decides to work, what I've got is that t squared is equal to 4 pi squared r cubed over g m s. Now this looks a lot like Kepler's third law, but we talked about 4 pi squared over gms as being c, or just a value for a constant. So 4 pi squared over gms is your c. Now, in this particular example, the ms is the mass of the sun, or the mass of the object that the satellite is orbiting around. But it doesn't always have to be the sun. This could be the Earth, and this could be a moon or something, or this could be Jupiter, and this could be a moon. Whatever the case may be, this is how you would arrive at your c constant if you're looking at 2 different things being in orbit, as opposed to like the planet and the sun. So, that's all I have for you guys tonight, and bring your book tomorrow. See you later. Bye.